the standard is the next generation Stein standard, that is develop models to illustrate the changes in composition of the nucleus of the atom and the energy released during the process of fission, fusion, and radioactive decay. So today's learning target is that I can define radiation and identify 3 types of radioactive decay. And I can define isotopes, I can identify the isotopes of carbon and how they are used to determine the age of fossils. This is a pretty basic relation to the standard. I have tried to make it simpler, and I haven't included any numericals because I want you to understand and keep it simple. So we are defining radiation, and radiation is the emission of and propagation of energy in the form of waves, rays, and particles. We'll go through this later in the lesson. Isotopes are the atoms with the same number of protons and electrons, but different number of neutrons. So we have stable and unstable isotopes. Some isotopes are unstable. These isotopes will be called radioisotopes, and the unstable isotopes, they emit energy in the form of radiations, and there are 3 types of radiations that are also called radioactive decay. So the first is the alpha decay. In alpha decay, there are positively charged particles, and when there are too many protons in the nucleus of the atom, they consist, the alpha particles, they consist of 2 protons and 2 neutrons, and they have a positive charge of +2. They are helium atoms with +2 charge, and they are called alpha. So you can see the alpha particle being emitted out of the nucleus. It's got 2 protons and 2 neutrons, and we don't have any electrons along with that, and so the positive charge for the alpha. Then we have the beta decay. The beta decay is caused when there are too many neutrons in the nucleus. The neutron splits into protons and negatively charged electrons. In this case, the element will emit radiation in the form of negatively charged particles called beta particles, or the electrons, and these are called beta rays. So you can see over here the neutron is splitting into the positive charged over there, and the negative electron is getting free. You can see it right at the bottom right hand side. Now we come to the gamma decay, and gamma decay is, this occurs when there is too much energy in the nucleus, and in this case gamma particles with no overall charge are emitted from the element. These are called gamma rays. So you can see the radiation being radiated out of the nucleus. There's no electron or proton that's coming out of this. It's just the atom that's at a higher energy level. It when it stabilizes, it releases energy, and that goes out in the form of gamma rays. In the visible spectrum, you can see that we have the visible light, and it can reach the Earth. And then we have the ultraviolet, the X-ray, and the gamma rays are really just too far on the left. The penetration is not much on the surface of the Earth. Just to make it slightly more interesting, the gamma rays, they are emitted when the stars collapse, and the pulsars, they emit really big bursts of gamma rays which can be lethal, and they can travel up till many light years. Luckily, there's no star which is collapsing near Earth. So now this is the radioactive material you can see, and you can see a lead block that's preventing the radioactivity from spreading, and the radioactive rays are there coming out, and we have an electric field in which we have a positive and a negative charge, and you can see the radioactive rays, they are deflected, and you have the beta particles going towards the positive charge. You have the gamma rays, which are neutral, and so they are going straight. They are not affected by either the positive and negative charge. And you have the alpha particles that are being deflected towards the negative charge. What difference do you see in the deflection and the pattern of deflection in the beta and the alpha particles? Can somebody please tell me? Yes.
The beta is a sharper incline away.
Yeah, so that's a perfect answer. So now, can you give me any reason for that?
No.
Well, okay. So the reason is that the beta particles, they are basically just light in weight, and so they are easily deflected. And the alpha particles, they are heavy. Like I told you, they are helium atoms without the electrons, and 2 protons and 2 neutrons are pretty much heavy and difficult to deflect. So this short video is going to just...
The British scientist Ernest Rutherford was one of the first to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays. Other experiments showed later that the beta rays are actually high-speed electrons. The alpha particles proved to be helium nuclei. The gamma rays are high-energy photons, analogous to X-rays.
So now we are seeing that we have carbon molecule that's depicted by neutrons and protons, and we can see the number of protons being as 6 shown at bottom, and the total mass of protons and neutrons as 12. Now we have this is an isotope of carbon, so this has, you can see instead of 14 we have, instead of 12 we have 14 neutrons and protons over here. So we are going to use this and see what radioactivity is. So nucleus of the atom, it undergoes decomposition to form different nucleus, and the decomposition, it means different forms of energy is released, and we already studied it, that there are alpha, beta and gamma rays, and there are positrons, but I haven't covered them over here for the simplicity. We see there's loss in mass when alpha particles, they come out of the element, and so here we see that uranium-238 and is basically emitting helium atoms, and we are getting a new element due to radioactivity, and you can also call this as fission. So you can have the carbon-14, and you can see that the naturally occurring carbon is carbon-12 can be depicted by the yellow carbons, but we have one carbon-14 that's available. Generally, you can say it's not in big quantities, but it is there in the nature. So how does this carbon-14 help us, and how will the radioactivity decay benefit us? Any ideas? Because radiation is usually not good for us. We usually associate it with bombs and all kind of stuff. So carbon-14, any idea how we can use the radioactivity of carbon-14 for our own benefit? Yes, please.
Does it have to do with CO2?
Well, yes. Indirectly, I would say yes. It's a start over here, CO2, because we have plants, and the plants are basically processing CO2 and they are converting it into energy, and it's being you can say carbon-14 is being taken by the plants, and it comes into the system, and then the animals, they are going to eat these plants, and it goes into the bodies. When we are alive, this process is continued, and so the carbon-14 in the body is constant, but after we die, we are not able to get this carbon-14 anymore. And we are able to determine the age of the fossils with this, so that's how you understand that this fossil is either 400 years old, or like most probably they are more than thousands of years old. And this is one use where we can benefit out of radioactivity. The other is that we say the iodine 133 is used to test the thyroid functions, and thallium-201 can be used for heart tissues after the heart attack. So now I'd like you to discuss with each other in small groups what you have actually learned, and then we can ask some of you to tell the rest of the class what you have actually learned.
Alpha is
have about 3 minutes.
yeah, it goes up much higher.
That was the alpha?
Beta.
Beta.
Beta goes up higher.
Yeah.
Sharply transmits.
Is that helium? Is that the alpha?
I don't know.
Helium's a gas.
Oh. Yeah. It's lighter.
I guess just that there's different forms of decay and radiation.
Carbon date things.
Yeah.
Small isotopes. Highlight your body.
Yeah.
And it's magic.
When that happens, like, doesn't like carbon dating, it's like halves itself each time.
One of my best friends is my lab partner, and that's the one
We discussed it afterwards
to get
because it's
together.
You don't remember that?
And that's how they figure out the fossils like 7 billion years old. Let's ask him. Does carbon like half itself every so often?
5,730 years.
Okay.
Carbon-14.
Yeah. Okay.
So that's how we calculate it when we measure how much is left. So it gives us a approximate idea that how much carbon is in the system. So would anybody like to share with the rest of the class what they have learned in this? Would anybody like to volunteer? Nobody? I found pretty nice discussions over here. Yeah, Zoe, please go ahead.
Share that story. He's supposed to be teaching high
Well,
school.
I just noticed that on the last slide it said something about thyroid and radioactivity, and my husband had thyroid issues and he had to take a radioactive pill.
Connection. Real world connection. That's 5D right there.
It worked.
So I hope you learned something about radioactivity in this.